All right, let's tackle it. Unit 3.3, Algebraic expansions and factorizations. So you might have been wondering what we were doing for the last couple days. Why we have been reviewing rules of exponents, right? And especially with some of the stuff that I was doing yesterday with the rational exponents, where I had you using the exponent rules with expressions that had fractions in them, and you were distributing things with negative exponents or distributing things with fractional exponents. Why? Well, the reason why is because you can, through manipulation, you can make equations that are not polynomials look like polynomials, and you could solve them the same way you would have solved polynomials. And this is a really powerful um, what's the tool? Tool word I'm looking for? Tactic. Let's use the word tactic. It's a really powerful tactic for solving strange equations. This one says to expand and simplify. Expand means, to basically FOIL. So we're going to just distribute. You can't even FOIL. You're going to distribute this x to the negative 1/2 to all three of these places. Now I'm not going to skip any work. I'm just going to show you what that looks like. So that gives us a x to the negative 1/2 times x to the 3/2 plus x to the negative 1/2 times 2x to the positive 1/2 minus x to the negative 1/2 times, and since I've already written the minus, 3x to the negative 1/2. Now, could I have written x to the negative 1/2 after all of those terms? Sure. I just chose to write it in the front because I'm weird. I don't know. It's just what I did. Okay, it doesn't really matter, right? You prefer the x to the negative 1/2? Yeah. The only time that it really causes an issue is when there's a constant already there. So it looks strange, especially when it's negative, because I had to move that negative sign in front of the x to the negative 1/2. My point is just watch your symbols, please. We need to be very, very accurate. Because if this is an IB question and I goof up the first line with the wrong symbol, basically I've gotten no credit for the entire question because that's bad method. We just want to be very careful with our symbols. So here, we're multiplying two things with the same base. When we multiply two things with the same base, what do we do with the exponents? You add them. So again, showing all the work. This is going to give me x raised to the negative 1/2 plus 3/2, and then plus the 2, the constant now belongs on the front. X to the negative 1/2 plus 1/2 minus, again, constant on the front. X to the negative 1/2. I could say plus negative 1/2, or I can just say minus 1/2. And we were just told to simplify. What is negative 1/2 plus 3/2? Yeah, it's going to give me 2/2, right? So it's just 1. This is x to the first power. Plus, what's negative 1/2 plus 1/2? 0. But what does x to the 0 equal? 1. So this is just plus 2. And then this last one, minus, negative 1/2 minus 1/2. That's just negative 1, right? I don't want to write minus 3 times x to the negative 1. I'm going to do this. Let's do it like that, so that way you understand why I'm writing it as 3 over x. So when we're simplifying, we don't want to leave answers with negative exponents. Now, if the directions were telling us, write that as a single power of 2 or something, yeah, sometimes negative exponents were forced. But now we're saying don't do that. Boom, there it is, right there. That's it. That's all you had to do. Talk to me. Is there anything we need to discuss? How did you get that? Or what did you do there? Or why didn't you do, anything. You guys, you talk to me. No? Okay. Any questions? I just repeated it. Any questions? Yeah. Yeah, no, I didn't have an actual question. All right, cool. So there it is. We just distributed and we used exponent properties. When you multiply two things in the same base, you add the exponents. And let's just not keep negative exponents in our answers. Now we're being told to expand and simplify again, but this part A, question A, we're foiling. Okay. The first green arch is 2 to the x times 1. That's just 2 to the x. What am I smoking? That's not the first green arch. I'm sorry. The first green arch is 2 to the x times 2 to the x. So I tell you what I'm going to do. I'm going to show all of the work. I'm going to show all of the work to make sure that we're all following along. Just going to foil it here. And then 3 times 1. There. So I haven't skipped any steps. Haven't skipped any steps. Anytime you write something times itself, what's an easy way to write that using symbols? Something squared, right? So anytime you multiply something to itself, you just are squaring that object, right? 4 times 4 could be written as 4 squared. X times x could be written as x squared. So 2 to the x times 2 to the x can be written as 2 to the x squared. 2 to the x times 1 is just 2 to the x. And guess what 3 times 2 to the x is? It's 3 times 2 to the x. You actually can't do anything with it. You can't do anything with it. Because they don't have the same base, they can't be multiplied. And then the last one's obviously just 3 times 1 is plus 3. Lastly, if I were to treat 2 to the x as green box, can we agree that this says 1 green box plus 3 green boxes? Can we agree to that? So that would give me 4 green boxes, correct? Okay. Clearly, I'm going to have to clear some stuff. But here's plus 4 green boxes. Ta-da. And you might be asking yourself, why would I have bothered doing that? What purpose would this serve? Well, it would help you solve equations that are written in exponential formats like this. Yes? The other 3, you mean, so this right here became that. Because I had 1 green box and I added 3 more green boxes, leaving me with 4 green boxes.
Mr. McCutcheon?
Yes, sir.
Couldn't you write the 4 as 2 squared and then combine 2 and the x?
Absolutely could. So we can take this even further. I could do what Chris said right there in the middle, and on the front, I have a power to a power. When I raise a power to a power, what does that give me? You multiply them. Whenever you raise a power to a power, you're supposed to multiply the exponents. Like I said, I'm going to have to clear this, okay? I'm writing really big. But whenever you raise a power to power, your job is to multiply the exponents. So you have 2 to the 2x plus. Now, Chris said, isn't 4 a base 2 number? Yes, it is. It is 2 to the 2. And since I'm out of vertical space, I'm just going to write equals, and I'm going to write it over to the right. So 2 to the 2x is what it is. It is 2 to the 2x. Let me scroll down so my people in the back can see. Now, in this middle, I have 2 things that are base 2 being multiplied together. And whenever you multiply 2 things with the same base, you add the exponents. That is a finished format. So if I were to have given you this equation, 2 to the 2x plus 2 to the x plus 2 plus 3 equals 0, soon you will be able to solve that equation without technology. And the way you do it is by manipulating this polynomial It's not a true polynomial. By manipulating this expression to look like a polynomial. Yes?
What exactly qualifies as a polynomial?
So in order for something to be a polynomial, every term has to be separated by pluses and minuses. So we have that. And we have to have variables that are x's that have integer exponents. So we don't have x's with integer exponents here. We have base 2's, which breaks the rules of polynomial. So polynomial would be constants sitting in front of x's, and those x's would have exponents. And those exponents have to be non-negative, and they have to be integers. So this is all kinds of not polynomial. But we could manipulate it to look like a polynomial, and then we could solve it. That's what we're getting at. But there we go. If you need to ask me anything about what just happened, it's time. That's the final answer. That's its final form.
So the x plus 2 just came from the
Yes. This right here, let me use a different color. This right here is the x plus 2 because I'm multiplying two things with the same base. That's why. Cool? Yes, Brian.
Right under the green box, where did you get plus 1?
The green, oh, no, okay, so what I was saying was if it was just green box, could we agree that that is one green box? That's all I was saying. It's like saying x. If I just say x, are you cool with the idea that there's sitting a 1 technically in front of it? It's the same idea. That's all I was saying. So I had one green box. What I'm doing when I say green box is I'm trying to get you to realize that 2 to the x is just an object, and that you had one of those objects, and you were adding 3 more of those objects, giving you 4 of those objects. I don't want you thinking of them as letters or thinking them as numbers. I want you thinking of them as objects, because all objects behave by the same rules in mathematics. Alrighty, so I'm gonna have to clear all that crud to do part B. So let's see here. Gigantic eraser, big, huge, and come on. What? Hold on. You listen to me, active panel. I am the boss. There we go. Okay. Part B. That exponent of 2 up there, yeah, you can't apply that exponent to those two terms inside those parentheses because those two terms are separated by pluses or minuses. So instead, what we have to do is realize that that 2 up there means you need to write this thing twice. It is this object times itself. And then we get to do the exact same thing we did in part A. We are going to FOIL. Right. We can't use, what they call that, the, what do you call that? It's like when you have a product raised to a power, then all the objects inside the parentheses get that exponent of 2. But this is not a product raised to a power. It's a set of parentheses with a plus or a minus in them. So the moment, it's like if I said x plus 1 squared. That's not x squared plus 1. You know, it's x plus 1 times x plus 1. So it's the same idea because that's a plus sign, not a multiplication dot. If it was a multiplication dot, then yes, I could have applied that 2 to both of those objects. So the first one gives me 7 to the x times 7 to the x. And again, I'm going to show all the work. And I'm going to give us a slightly different way of thinking about this 7 to the x times 7 to the x in just a second. And then I have plus 7 to the x times 7 to the negative x plus 7 to the negative x times 7 to the x plus 7 to the negative x times 7 to the negative x. There. Rather than do what we did last time and say, hey, look, technically when you multiply an object to itself, isn't that thing squared? Why don't we do it like this? Can we agree right here that this 7 to the x and this 7 to the x at the front, that they have the same base? So when you multiply two numbers with the same base, what do you do with the exponents? You add them, and what's x plus x? It's 2x. So this is going to give me 7 to the 2x plus. All right, well, same idea. Add those two exponents. What does x and negative x give you? 0. So this says 7 to the 0. And Well, so does this. But what does 7 to the 0 equal? Equals 1. So both of those 7 to the 0s become 1. And at the end, negative x plus negative x is negative 2x. Well, anything with a negative exponent belongs in the bottom of a fraction bar, so that way we can give it a positive exponent. Basically, anything with a negative exponent needs to move across its own fraction bar. So what we have here is 7 to the 2x plus 2 plus 1 over 7 to the 2x. I think that one was actually easier than the first one. Because the first one's got some trickery in it where you go, oh, that 4 is a base 2 number now. Like, that's kind of tricky. It really is. So what would have made you realize that? What would have made that more obvious? How about practicing factoring? You see, because you wouldn't have thought to combine those two things until you had gotten used to the fact that they could have been taken apart. At least that's the way I think about it. So let's factor some crap. Here we go. Look at all this stuff down here. We're going to factor these things. Things that you didn't know you could factor. No, these aren't polynomials. No, these aren't quadratics. But yes, you can factor them. A. Instead of writing it as 2 to the n plus 3, I would like you to remember the exponent rule that says when you multiply two numbers of the same base, you add their exponents. Well, here I have an addition in my exponents. What that means is that first term can be taken apart to be 2 to the 3 times 2 to the n. Because when you multiply two numbers of the same base, you add their exponents. And addition doesn't care about order, so I move the 2 to the 3 to the front. Awesome. We were told to factor. The very first thing you should do anytime you're factoring is look for a GCF. I see a GCF. It's 2 to the n. So I can factor a 2 to the n away from both of these terms. When I pull the 2 to the n away from the first term, all that's left is a 2 to the third. And the last one is going to be a 1. I'm undistributing. But what is 2 to the third? It's 8. 8 plus 1 is 9. So our answer is 9 times 2 to the n. That is actually factored. Isn't that weird? It's crazy, isn't it? I factored, but then it simplified, which is kind of neat. If something up there is not making absolute perfect sense, you say something to me, you talk to me, you let me help you. And again, you're wondering, why would I ever do this? And the only reason why you would ever do it is so that you had the ability to solve equations like this. And that is coming up very, 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 very soon. Okay, then let's do part B. Let's do the exact same trick. That 2 to the n plus 3, yeah, I'm going to call that 2 to the third times 2 to the n. And this time, I'm like, oh, well, I don't see a GCF yet. But 2 to the third is 8. And now I see a GCF. That GCF is 8. So I factor out the 8. I'm dividing both the terms by 8, and it leaves me 2 to the n, plus 1. And, well, that's it. It's factored. Ta-da, done. Can't do anything else. Now this last one. I'd be curious to know, does anybody see what the GCF is? It's not 2 to the n.
Is it 4?
It's more than that. It's 2 to the 2n. That is the GCF. But why? Why? Okay. You guys were comfortable with what I did in part A and part B, where I had that 2 to the n plus 3, so I separated that into 2 to the n times 2 to the third? That was cool, right? Well, then why don't I call 3n 2 to the n plus n? Which can be rewritten. It's not really simplifying. It can be rewritten as 2 to the 2n times 2 to the n. And now 2 to the 2n is my GCF. Like that. By the way, 2 to the 2n could be written as 4 to the n, because 2 squared is 4, but that doesn't help us any, so there's no point in doing it. So that one's a little bit harder to see. And that's why we practice things like this. You want them to jump out at you as something that is factorable. Because very soon, you will be factoring things that you didn't know you could factor, and you will be solving them in ways that you didn't know were possible. I would also like to bring to your attention that you realize that I didn't use anything more than Algebra 2 skills to pull this off. You're gonna see that there's a lot of things I show you this year that are just new ways of using knowledge you already have, that you didn't know you could do. You didn't know that you could factor exponential equations, did you? But you can. So let's see what else we got going on. Come on, active panel, catch up with me. There we are. Let's continue factoring some stuff. What jumps out at you about these two terms? Not how are you supposed to factor, but I'm just asking you what jumps out to you. They're both squares. This is the difference of two squares. Maybe you're like, well, like Ashley B said, how are we supposed to factor it? We recognize it as a difference of two squares, but maybe we should manipulate it first so it's more obvious that it's a difference of two squares. Instead of writing 4 to the x, just a moment ago I told you that 2 to the 2n was 4 to the n, right? So instead of saying 4 to the x, we could say 2 to the 2x minus 9, because 2 to the 2 is 4. And instead of writing it as 2 to the 2x, you can instead write it as 2 to the x squared. And hopefully now it is obvious that it's a perfect square minus perfect square. And just to remind you, a squared minus b squared is equal to a plus b times a minus b, something we learned about in Algebra 1. This time, a happens to be 2 to the x, and b is 3. Like that. That's what it factors to. I absolutely love question B. Just love it. Would you believe me if I told you that question B is quadratic in nature? It behaves like a quadratic. It could be treated as a quadratic. And here's how. Hopefully you notice that there's a 9 to the x and a 3 to the x. See, that wasn't an accident. And it's not an accident that 9 is a perfect square. So instead of saying 9 to the x, I'm going to say 3 to the 2x And then I'm going to do the same thing that I did over here, where I remember that a power raised to a power would force me to multiply those exponents. So I want to take apart the multiplication of exponents, and I want to write it like this. 3 to the x squared plus 4 times 3 to the x plus 4. And you're looking at that and you're going, I don't see it. Maybe some of you are seeing it now. Yeah, that is quadratic-ish. So I could treat it as a quadratic, and maybe some of you aren't. So for those of you that aren't, let me introduce you to an idea that is very powerful in mathematics and will be used a lot when we get to calculus, known as substitution. Why don't we make a substitution that makes our life a little bit easier for those of us that are struggling to see it? Why don't we say something like, why don't we just come up with a new variable? Let's let m equal, because McCutcheon, let's let m equal 3 to the x. If m equals 3 to the x, I think we can all agree that this says m squared plus 4m plus 4. And you should be able to easily factor that. I'd be looking for the two numbers that multiply to be 4, that add to be 4. 2 and 2, yeah. So this would give me m plus 2 times m plus 2, which is the same thing as saying m plus 2 squared. And last but not least, resubstitute for m. Oh, look, attendance is booping me. Let's see. Our very last step would be to resubstitute for m, because there were no m's in the original equation. It was 3 to the x. So this factors to be a straight line. This factors to be 3 to the x plus 2 quantity squared. Isn't that neat? Isn't that neat? So yeah, it behaves like a quadratic, and it can be worked on like it is a quadratic. It's not, but you can treat it like one, and you can work on it like one, which means you could solve it like one as well. Could we use the quadratic formula? Yes, we could. We won't, but we could. Before I move on, these are weird, abstract concepts. I'd be asking you to talk to me. You have to be able to pull this off to do questions on your test. They're part of the process. They are not the whole process. They're part of the process. You don't have to substitute. That's not a necessary step, but it does help people see how to factor. So even though it's a good method, it's not one that's required, so IB doesn't give credit for it. Now, when we get to calculus, there are plenty of questions where substitution was necessary, and you have to show it. So I start showing it now because, like, look, substitution's a fantastic method. It works all the time. It works a lot of the time. Yes, Gabe.
So like on the ID exam,
Mm-hmm.
we had to like factor out like that.
If you had to factor,
Would we have to write like m equals 3x, or
if you're going to change the variable, you need to write why you're doing that. Otherwise, it's not viable method. But if you were to write let m equal 3 to the x, now the grader goes, okay, this student is altering the variable structure. But if you just change letters and things got different on you, and you don't show why, it's going to ding you bad. Because you didn't have to do that. That's the thing. On an IB style question, it would have jumped from here to here, just like that, and nothing in between would have been worth anything. Because at that point, it would have been quote unquote obvious that it was a perfect square trinomial-ish thing to them. So. And I believe, oh, no, that's not the end. Cool. I love this lesson, by the way. Simplify. Guess what it's not? It's not 2 to the n. You can't do that. You can't do that. But you can manipulate these things. Or maybe it is 2 to the n. I don't remember. I'm being real. You see I'm not holding my notes? I don't remember. Let's go ahead and do this. What can we do? We can manipulate it. Oh, the answer is 2 to the n. But why? The answer is 2 to the n, but why? Hey, do you guys remember that rule that says if you raise a fraction to an exponent, both the top and the bottom of that fraction get that exponent. So isn't it true that I could write this as 6 over 3 all raised to the n? What 6 over 3 is 2. I spoke before I looked. So yeah, you can, what did we do here? We divided the exponential bases, but we were only able to do that because the exponents matched. We divided the exponential bases because the exponents matched. That allowed us to do that. So what should the next one be then? 2/3 raised to the n, which would be 2 to the n over 3 to the n, right? But that's because we can write this as 4 over 6 to the n, which is 2 over 3 to the n, or 2 to the n over 3 to the n. And those skills are vital. And those skills are necessary to pull off these last 3 questions. These are the last 3, correct? Yeah, okay. We need to be able to do that. It's like playing a game of pulling an exponent from a fraction. Yes, sir?
You have to show all that work, but could you just divide the 46 by 2?
It depends on what the question says on the test. Remember, the question would never be just that. But if it says find, or if it says simplify, I would show my method just in case I do something wrong. Is it going to be a required step? Probably not, but you can never know. I never know what's going to be a required work step and what's going to be something that is implied work step. I have no clue. So because of that, I just always show my work. Because like I said, when I give you guys, if it's a brand new test, I take the test. I always take the test with my students just so I can make sure it was fair time-wise and make sure that there was no mistakes on it and things like that. So if it says find, or if it says simplify, or if it says solve, my advice is just show all your work. Just show it all. It didn't take much effort to do that. All right, let's pull these off. See what we can do. It says to simplify. All right, well, what you can do is you can separate this into 2 fractions. They have the same denominator. So you can write it as 3 to the n over 3 to the n over 3 to the n plus 6 to the n over 3 to the n. Well, anything divided by itself is just 1, right? Anything divided by itself is just 1. And we just saw that if you have a fraction and the top and bottom have the same exponent, you can basically just reduce that fraction. We can call that 6 to the n over 3 to the n. We can call that 6 over 3 to the n, which is 2 to the n. Something interesting just happened. Something interesting just occurred that we didn't see happen in the notes before, and I'd like to draw your attention to it. You saw me take a fraction that had the same exponent on the top and bottom and move that exponent outside of parentheses, right? You saw me do that? Well, if I could do it with quotients, I can also do it with products. So that 6 to the n could have been thought as being, so this is an aside that would have made this question maybe a little bit easier. I don't know what you think is easy or not, but 6 to the n can be thought of as 2 times 3 to the n, which is 2 to the n times 3 to the n. And if I had written my 6 to the n as 2 to the n plus, or times 3 to the n, if I had written it like that on the top of my fraction bar, then I could have factored that 3 to the n out as a GCF and then canceled it. I don't know what you think is easier. You're welcome to separate it and simplify it, or factor it and simplify it. It's completely up to you. You saw me separate and simplify, but I did that just so I could bring to your attention that clearly there was something going on between that 6 and that 3 that gave me that 2. There must have been a way to factor it out as a GCF. I'm going to use that knowledge for part B, just so you can see it in work. All right. 2 to the m plus 2. I would like to use that 2 to the, or write that 2 to the m plus 2 as 2 to the m times 2 to the 2 minus 2 to the m divided by 2 to the m. I see a GCF. On the top of this fraction bar, there's a GCF of 2 to the m. So let's factor that 2 to the m out, leaving me a 2 to the 2 minus 1 over 2 to the m. And check this out. Just leaves me 4 minus 1. Would you have had any idea that that equals 3? But it does. Mental math did, this guy. But yeah, it equals 3. Neat, right? So neat. Man, I'm a nerd. I love neat math. Let me give myself a little bit more space here. Necesito más espacio. Let's change this white. There we go. And the last one, which I can't remember. Alrighty. All right, so that 2 to the m plus 3, that can be written as 2 to the m times 2 to the 3 plus 2 to the m over 9. I want to say that there's probably a mistake in that question. But before I go any further, I'm going to double check my records to see if there's a mistake. Okay, good. So I have not made a mistake anywhere. I thought maybe I did. I made the mistake years ago, but I have since fixed it. So we are okay. We are in the clear. I'm going to leave this 9 a 9 for now. Yeah, I'm going to leave this 9 a 9 for now. Now, on the top, this 2 to the m, the 2 to the m can be pulled as a GCF. So I get 2 to the m. What it leaves me inside is a 2 to the 3 plus 1. And 2 to the 3 is 8. 8 plus 1 is 9. So 9 times 2 to the m over 9 equals 2 to the m. There we go. Woot. So much fun.